ഹലോ സാറേ കേൾക്കാമല്ലോ സാറേ? സാറേ ഒരു 1-2 മിനിറ്റ് കൂടെ ഒന്ന്, കാരണം ആൾക്കാരെല്ലാം ജോയിൻ ചെയ്തുകൊണ്ടിരിക്കുവാണ്. മിന്നു, നിങ്ങളുടെ കോളേജിൽ നിന്ന് എല്ലാവരും ആയോ? മിന്നു
ആയി സാറേ.
അജീന, പത്തനംതിട്ട? അൻസലെ, മണിനിലക്കുന്ന്? അൻസൽ ഉണ്ടോ? അൻസൽ കയറിയിട്ടുണ്ടോ? ഹലോ അൻസൽ, മണിമലക്കുന്ന് ആരാ ഉള്ളത്? ഈ ലേണിംഗ് സെന്റർ ഏതാണ്? ആരുടെയാണ്? ശരി, ഓക്കെ. അപ്പൊ നിങ്ങളുടെ കുട്ടികളെല്ലാം അതിനകത്തുണ്ടല്ലോ അല്ലേ? മണിനിലക്കുന്നിൽ ആരാ ഉള്ളത്? മണിനിലക്കുന്നിൽ അൻസലെ? കുട്ടികളെല്ലാം ആയോ? നമ്മൾ തുടങ്ങാൻ പോവാണേ. നാളെ നേരത്തെ കയറണം എല്ലാവരും. 10:50 ആകുമ്പോൾ കയറിയിരിക്കണേ, കാരണം നമുക്ക് സാറിന് നല്ല തിരക്കുണ്ട്. അപ്പൊ നമ്മളിപ്പോ ഞാൻ സ്റ്റാർട്ട് ചെയ്തോട്ടെ? സാറേ നമ്മൾ സ്റ്റാർട്ട് ചെയ്യാനായിട്ട് പോവുകയാണേ. തുടങ്ങാം. അപ്പോൾ ഈ വർക്ക്ഷോപ്പിലേക്ക് എല്ലാ ഫാക്കൽറ്റി മെമ്പേഴ്സിനെയും വിദ്യാർത്ഥികളെയും എക്സ്പെർട്ട് കമ്മിറ്റിക്ക് വേണ്ടി സ്വാഗതം ചെയ്യുകയാണ്. നമ്മളെല്ലാം മനസ്സിലാക്കിയിട്ടുള്ളത് പോലെ ഇന്നും നാളെയുമായിട്ട് വിജയമോഹനൻ പിള്ള സാറ് ഈ ഗ്രട്ടൽ ഉപയോഗിച്ച് എങ്ങനെയാണ് ടൈം സീരീസ് മോഡലിംഗ് നമുക്ക് നടത്താൻ കഴിയുക എന്നുള്ളതിനെ കുറിച്ച് ഒരു വെബിനാർ നിങ്ങൾക്ക് നൽകുന്നതായിരിക്കും. വിജയമോഹനൻ പിള്ള സാറിനെ കുറിച്ച് ഞാൻ യഥാർത്ഥത്തിൽ പറയേണ്ട ഒരു ആവശ്യമില്ല. സാറ് നമ്മുടെ ഇന്ത്യയിലെ തന്നെ ഏറ്റവും ശ്രദ്ധേയനായിട്ടുള്ള ഇക്കണോമെട്രീഷ്യനാണ് വിജയമോഹനൻ പിള്ള സാർ. അദ്ദേഹം ഒരു തിയറട്ടീഷ്യൻ കൂടിയാണ്. അദ്ദേഹം നിരവധി പേപ്പറുകളും ഗവേഷണ ലേഖനങ്ങളും എല്ലാം തന്നെ വിവിധ ഇക്കണോമെട്രിക് ടൂളുകൾ ഉപയോഗിച്ച് പബ്ലിഷ് ചെയ്തിട്ടുള്ള സ്കോളറാണ്. അദ്ദേഹമാണ് യഥാർത്ഥത്തിൽ ഇക്കണോമെട്രിക്സ്, ഈ ടൈം സീരീസ് ഇക്കണോമെട്രിക്സ് നമ്മുടെ കേരളത്തിലെ സർവകലാശാലകളിൽ ഇൻട്രൊഡ്യൂസ് ചെയ്യുന്നതിന് അദ്ദേഹത്തിന്റെ സാന്നിധ്യം ഒന്നുകൊണ്ട് മാത്രമാണ് നമുക്ക് കഴിഞ്ഞിട്ടുള്ളത്. നമ്മുടെ കേരളത്തിലെ സർവകലാശാലകളിൽ ടൈം സീരീസ് ഇക്കണോമെട്രിക്സ് ഒരു കമ്പൽസറി പേപ്പറായിട്ടുള്ളത് MG യൂണിവേഴ്സിറ്റിയിൽ മാത്രമാണ്. അന്നത്തെ ആ ബോർഡിന്റെ എക്സ്റ്റേണൽ എക്സ്പെർട്ടായിട്ട് പ്രവർത്തിച്ചത് വിജയമോഹനൻ പിള്ള സാറാണ്. ഞാനും ആ ബോർഡിൽ ഉണ്ടായിരുന്നു. ഞാൻ ഇക്കണോമെട്രിക്സ് പഠിച്ചത് വിജയമോഹനൻ പിള്ള സാറിൽ നിന്നാണ്. അപ്പോൾ സാറാണ് നമ്മളെല്ലാം തന്നെ ഈ മേഖലയിൽ നയിച്ച് മുന്നോട്ട് കൊണ്ടുപോകുന്നത്. ഇപ്പോൾ ഈ MA ഇക്കണോമെട്രിക്സ് എന്ന് പറയുന്ന പുതിയ കോഴ്സ് യൂണിവേഴ്സിറ്റിയിൽ ആരംഭിച്ചപ്പോൾ അതിന്റെ അതിന്റെ എക്സ്പെർട്ട് കമ്മിറ്റിയുടെ കൺവീനർ ആകാൻ എനിക്ക് യഥാർത്ഥത്തിൽ പ്രചോദനമാവുകയും ധൈര്യം നൽകുകയും ചെയ്തത് വിജയമോഹനൻ പിള്ള സാറിന്റെ സാന്നിധ്യമാണ്. വിജയമോഹനൻ പിള്ള സാർ ഇല്ലായിരുന്നെങ്കിൽ ഞാൻ ഇതിന്റെ എക്സ്പെർട്ട് കമ്മിറ്റിയുടെ കൺവീനറായിട്ട് ഞാൻ വരികയോ ഇതിന് മുമ്പിൽ നിൽക്കാൻ എനിക്ക് കഴിയുകയോ ചെയ്യുമായിരുന്നില്ല. അദ്ദേഹമാണ് ഈ നമ്മുടെ സിലബസ് തയ്യാറാക്കുന്നതുമായി ബന്ധപ്പെട്ട് എല്ലാ മാർഗനിർദ്ദേശങ്ങളും നമുക്ക് നൽകിയത്. അതിന്റെ സിലബസ് ഓരോ വരിയും വായിച്ച് അതെല്ലാം തന്നെ ശരിയാണ് എന്ന് ഉറപ്പുവരുത്തിയത് വിജയമോഹനൻ പിള്ള സാറാണ്. അദ്ദേഹത്തിന്റെ സാന്നിധ്യം ഇല്ലായിരുന്നെങ്കിൽ ഈ കോഴ്സ് ഡിസൈൻ ചെയ്യാൻ കഴിയുമായിരുന്നില്ല. സാറ് നമുക്ക് എല്ലാവർക്കും അറിയാവുന്ന പോലെ CDSന്റെ പ്രൊഫസറായിട്ട് റിട്ടയർ ചെയ്തു. അദ്ദേഹം ഇപ്പോൾ ഗിഫ്റ്റില് ഗുലാത്തി ഇൻസ്റ്റിറ്റ്യൂട്ട് ഓഫ് ഫൈനാൻസ് ആൻഡ് ടാക്സേഷനിൽ വിസിറ്റിംഗ് പ്രൊഫസറായിട്ട് പ്രവർത്തിക്കുകയാണ്. വളരെ ബിസി ഷെഡ്യൂളിനകത്താണ് സാർ വർക്ക് ചെയ്യുന്നത്. സർക്കാരിന്റെ വളരെ പ്രധാനപ്പെട്ട പ്രോജക്റ്റുകളെല്ലാം തന്നെ നേതൃത്വം നൽകുന്ന അദ്ദേഹമാണ്. അപ്പോൾ നമ്മളോടുള്ള സ്നേഹം കാരണമാണ് ഇപ്പോൾ ഇതിനകത്ത് ഈ ഓരോ മണിക്കൂർ വീതം നമുക്ക് വേണ്ടി ചെലവഴിക്കാനായിട്ട് അദ്ദേഹം എത്തിച്ചേർന്നിട്ടുള്ളത്. ഫെബ്രുവരി അവസാനം അല്ലെങ്കിൽ മാർച്ച് മാസം അദ്ദേഹത്തിന്റെ നേതൃത്വത്തിൽ നമ്മളൊരു 1 വീക്ക് വർക്ക്ഷോപ്പ് നടത്തുന്നതായിരിക്കും. സാർ അതിന് സമയം തന്നിട്ടുണ്ട് എന്നുള്ള കാര്യം കൂടി ഞാൻ അറിയിക്കുകയാണ്. അപ്പൊ ഇനി ഞാൻ മറ്റൊരു ഇൻട്രൊഡക്ഷൻ നൽകുന്നില്ല. സാറിന്റെ മഹനീയ സാന്നിധ്യത്തിന് എല്ലാവരുടെയും പേരിൽ ഞാൻ നന്ദി പറയുകയും അദ്ദേഹത്തെ ഈ വെബിനാർ നടത്തുന്നതിലേക്ക് സ്വാഗതം ചെയ്യുകയും ചെയ്യുകയാണ്. സാറേ, നമുക്കൊന്ന് ആരംഭിച്ചാലോ? തുടങ്ങാം സാർ.
Good morning, everybody. Thanks, Santosh. So, I shall directly go to Gradle. You are all familiar with the Gradle, right? And you have already downloaded the package. So, I'm a little, so I'm familiar only with the Zoom, and here we can have present now, right?
സാറേ ഞാൻ ഒരു കാര്യം പറഞ്ഞോളൂ സാറേ.
Ah,
സാറേ ഞാനിപ്പോ ഇവരോട് പറഞ്ഞിരിക്കുന്ന സാറ് കാണിക്കുന്ന സ്റ്റെപ്പുകളെല്ലാം എഴുതിയെടുക്കണം എന്നാണ് പറഞ്ഞേക്കുന്നത്. പിന്നെ ഗ്രട്ടൽ എല്ലാവരും ഡൗൺലോഡ് ചെയ്തിട്ട് ഉണ്ടാവും, എല്ലാവരുടെയും കയ്യിലുണ്ടെന്ന് തോന്നുന്നു. പക്ഷെ എന്നാലും എല്ലാം എഴുതിയെടുക്കാനാണ് ഞാൻ പറഞ്ഞത്.
എഴുതിയെടുക്കുന്നതാണ് നല്ലത്. ഇത് സോ എങ്ങനെയാണ് നമ്മൾ ഈ എന്താ ഷെയർ സ്ക്രീൻ ഉണ്ടല്ലോ
സാറേ, ആ ഷെയർ സ്ക്രീൻ സാറേ, അതായത്
പ്രസന്റിൽ പോയിട്ട് എ വിൻഡോ അല്ലേ,
എ വിൻഡോ എടുക്കണം സാറേ. ഫുൾ സ്ക്രീൻ കൊടുത്തോ സാറിന്റെ, അതായിരിക്കും നല്ലത് സാറേ.
യുവർ എൻ്റയർ സ്ക്രീൻ,
എൻ്റയർ സ്ക്രീൻ അതായിരിക്കും സാറേ നല്ലത്.
സെലക്ട് വിൻഡോ ഓർ സ്ക്രീൻ. അത് കിട്ടുന്നില്ല
സാറേ. അതായത് നമ്മള് പ്രസന്റ് നൗവിൽ എടുക്കുമ്പോൾ യുവർ എൻ്റയർ
So now it is visible, right?
ഇപ്പൊ വിസിബിൾ ആ സാറേ, ഇപ്പൊ വിസിബിൾ ആ, വരുന്നുണ്ട്.
Okay, I shall start with a data set having these variables. Okay, this is a monthly data. The variables are W, R, M, and so on. Okay, I will start with this. Now I am opening Gretel. It is already here. You can see this, right?
കാണാം സാറേ, കാണാം.
Okay. So we have to enter the data. Entering data is very easier in Gretel. Okay. So you can see my desktop, right?
കാണാം സാറേ, കാണാം.
So if you have your data on the desktop, then entering data into Gretel is very easy. So what we have to do is just to click here. This is the data that I am using, this one. Okay, click here and drag it like this, and then drop it onto the Gretel window here. Okay, so dragging and dropping the data. So then release the mouse, and we have the Excel file here. I have a number of sheets here, and I am selecting this one, time series. Okay, if we have only one sheet on the Excel file, then it is very easier. We can just give OK. Otherwise, we have to select the concerned file, concerned sheet, and then click OK. So I am clicking OK. So all the variables are here. Now the Gretel will ask us whether you have a cross-section data or time series data or panel data, and we have to specify that. For that we have to give yes here. So click yes and then specify which data we have, cross-section or time series or panel. So we have a time series data, so click this one and click forward, this one. We have a monthly data starting from 1960 January. So click monthly and then forward. Okay, it appears 1960-01, that is 1960 January monthly data. We can change the dates. Here we have an up arrow and here we have down arrow. Using that we can change the start date, or we can just type it here. We can just type what we want. We can just type. Anyway, I am keeping it as 1960 January and clicking forward, and then we can apply the data. So here we have the sample from 1960 January to 1984 October. So we have the data set like this. Now click apply. So here we have all the variables. Now earlier these menus were not, these buttons were not visible. Now they have become visible. Now the first one is, once we have got a data set, then essentially we have to find out the time series plot of that variable, that time series. So I am clicking this W, highlight this W and go to the variable. Okay, before coming to the time series plot, okay, okay, let us take the time series plot. Click this one, time series plot, and we get the time series plot here. And we can edit this one. If we right click, we will get this one, and then we can edit it. Okay, we can edit the figure. And then we can copy, right clicking, we get this also, then click to this, copy to clipboard with a color or single color. We can copy paste this onto the board. So I think you are familiar with the time series plot of a variable like this. Here what we can find is, whenever the time series, this 0 is the mean of the time series. Whenever there is a deviation for the variable away from the mean, it will come back to that and it goes down. Then again it will go back to the mean. So we have a large number of reversions to the mean. That is mean, that is the variable is reverting to the mean, coming back to the mean. It is called mean reversions. If we have a large number of mean reversions like this, then this variable is, or this variable can be taken as stationary. So this is a stationary series. This is one way of tentatively finding out whether a series is stationary or not. Tentatively, because sometimes even though it may look somewhat stationary, the variable may not be stationary. We have to do some other tests. So we will come back to that later. That is, we have what is called a correlogram. Correlogram includes two graphical devices, that is autocorrelation function and partial autocorrelation function. We will come back to that later. Okay, anyway, this appears to be a stationary series. Now I am taking another one, say this fourth one, Ri. Go to the variable, time series plot. This 0 is the mean. 0 is the mean. But we find very few, one here and here, very few crossings. Very few crossings here. So that means it is not a stationary series. Moreover, here we have a fall. It may be a break in the time series, or it may be a property of the non-stationarity itself. So this series is not stationary. So we have to get the time series plot of any variable first to see whether it is stationary or not, tentatively. Because the time series plot will only help us tentatively to get a conclusion that it is stationary. So if we have something like this is non-stationary. I shall give one more example. Say this R. Go to the variable time series plot. See, we have a number of crossings, number of mean reversions. So this may be stationary. But what about this one? Mi. Go to the variable time series plot. See, we have again only very few crossings, very few crossings. So evidently this is not stationary. And one more, go to the variable, then time series plot. What about this one? This also looks stationary. Okay. So once we have time series, then with the gradle we have to see whether we have to get the time series plot to see whether it is stationary or not. Then some other cases also I shall tell you. See, for example, for this W, go to the variable, we can find the summary statistics. So whenever you have the data, you have to report the summary statistics. So get the variable, go to the variable and then summary statistics, click it. We have the mean, median, minimum, maximum, standard deviation, coefficient of variation, skewness, excess, kurtosis, and so on, percentages also. So this essentially, whenever we go for a data analysis, we have to give these summary statistics. Then we can also go to the variable and we can also have frequency distribution. Getting frequency distribution, you are familiar with the frequency distribution. That is, we are arranging the values in some concise, brief form with values arranging in different class intervals. And for every class intervals, we will have certain frequencies. So getting frequency distribution in gradle is very easier. Unlike in strata or spaces, those familiar with spaces can understand that. Now just click here frequency distribution and we get something like this. This number of bins means number of class intervals. By default, gradle has selected 17, but we can reduce it. Okay, we can have 11 class intervals. And you need not do anything else, just click OK. And here we have the frequency distribution with the 11 intervals, class intervals, and the midpoint and the corresponding frequencies. Then we have the relative frequency also and the cumulative relative frequency, and a small representation of this bar diagram here. Okay, we have a bar diagram also that will help us whether the distribution is normal or not. Okay, whether the distribution is normal or not. The normality we can also test using the normality test, or we can go for the summary statistics and see the skewness measure and the excess kurtosis. Let us do that. For example, go to the variable summary statistics. See, we have the skewness minus 0.1064. So this is a little negative, but it is not a very big number. It's not a very big one. So the skewness is somewhat less. Similarly, the excess kurtosis minus 0.038. That also is very small. So that means it may be the variable may be a little normal. So we can find out we can go for the normality test. Go to the variable, then here we have the normality test. In the normality test, usually the last one is the one that we use. Raki-Bera test. Okay, Raki-Bera test. So in this, the p-value is 0.747. Now remember, for the normality test, our null hypothesis is that the series is normally distributed, or the skewness measure is 0 and the kurtosis measure is 3. For a normal distribution, the kurtosis measure is 3 and the skewness measure is 0. Combining these two, we have the test, the Raki-Bera test. We combine in Raki-Bera test both the skewness test and the kurtosis test. And the null hypothesis is the variable is, or the series is, normally distributed. If the p-value is greater than 5%, then we do not reject the null hypothesis. That means our series is normally distributed. Here the p-value is 0.747 or 0.748. That is much greater than 5%. 5% means 0.05. So this is much greater than 5%. That means we do not reject the null hypothesis of normal distribution for the series. So this distribution, this series is normally distributed. Okay, and that is why I told you earlier, when we had got the frequency distribution, okay, with 17 we have this one. So it gives a somewhat normal distribution. A little negativities, that's all. But that negative skewness is not statistically significant. So this will give us that, see, this shows that this is a little normal. But statistically it is a normal distribution. Now, the stationary series, among the stationary series, you know, we have two cases, and the one case is the usual stationarity, and another is a process called white noise. For a white noise, we have three Euler's assumptions satisfied. That is, we have three assumptions of zero mean, then constant variance, that is homoscedasticity, and the third condition is that there is no autocorrelation. So no autocorrelation, no heteroscedasticity, along with the zero mean will give us a stationary white noise. This white noise is the name in time series. In general econometrics, we call this spherical error. You may have studied that. A spherical error term is one with zero mean, no heteroscedasticity, and no autocorrelation. And in time series, a spherical error is called a white noise. So to find whether a series is white noise or just stationary. Okay, so see, a white noise is a stationary series, but a stationary series need not be white noise. That means all the stationary series cannot be white noise. White noise is only a subset of the stationary series. And for the white noise, we have to, for a stationary series, we have to find out whether it is white noise or not by checking, and that we check using what is called the correlogram. So the correlogram is used to find out whether a series is just stationary or white noise or non-stationary. Okay, these three cases we can find out using the correlogram, and the correlogram appears in terms of graphical representation of two measures of autocorrelation function and partial autocorrelation function. Now let us see for this series W, what will be the correlogram. We go to the variable. Here we have the correlogram. Okay, just click this, and now for the correlogram we have to give some lags, because the correlogram or the autocorrelation function or partial autocorrelation function are functions of lag. As lag changes, the value, the autocorrelation value or the partial autocorrelation value also will change. So we have to give a lag. By default, Gretel takes 2 years lag, that is 24 lags. Remember, we have a monthly data. So 2 years means 24 lags. Just click that. Okay. Click OK. And here we have the graphical representation of ACF, autocorrelation function, and partial autocorrelation function. And we have the actual values also. And whenever there is a star in ACF or BACF or this Q statistic, the Q statistic along with the P value are given here. Whenever there is a star, that means the null hypothesis of no autocorrelation is rejected. And here we have one case, one star. One star means 10% significance. 2 star, and it is given here. See, 1 star means 10%. 2 stars like this means 5% significance, and the 3 stars means 1% significance. This is only 10% significance, and we usually consider the 5% significance level only. So if we take the 5% significance level, both ACF and PACF, we do not reject the null hypothesis. Okay, null hypothesis of no autocorrelation. So there is no autocorrelation. Here the p-value, all the p-values for the Q statistic. Q statistic combines all the ACF across that different lag. Okay, different lag of the ACF. That is the Q statistic. All the p-values are greater than 5%. Greater than 5% means we do not reject the null hypothesis. What is the null hypothesis? It is that there is no autocorrelation. So if there is no autocorrelation, then that means the series is white noise. And that is what we find here. We have 2 red lines. These 2 red lines are the 95% confidence interval. That is our level of significance is 5%. And these green spikes, these are the green spikes. These green spikes denote the different autocorrelation function, and here these are the partial autocorrelation function. For example, at lag 1, this is the autocorrelation value, that is this 0.0231, that is given by this one. Then the next one at the lag 2, 0.0185, that is this. And then we have 2, 3, 4, 5. At lag 5, we have this minus 0.0775, that is this. So all these are given here. Now, how do we find out whether these autocorrelations are zero statistically? These autocorrelations are zero statistically if they lie within the 95% confidence interval. So here we find that all these autocorrelations are within the 95% confidence interval. That means they are statistically zero. So this autocorrelation, all these autocorrelation values are statistically zero because they lie between the 95% confidence interval. Same is the case here. these partial autocorrelation functions are also within the 95% confidence interval. Therefore, they are also statistically zero. And here we have a marginal one, but this is significant only at 10% level. So we do not do not bother about this. And again, we take the Q statistic. Usually, it is the Q statistic that we mostly depend on, and the p-value shows that there is no autocorrelation at all at any level. Okay, so this W is a white noise. This W is a white noise. White noise means it is stationary also, but it is a limited subset of the stationary series. So this is how we find out whether we have a white noise or not using correlogram. Okay, we can also test the autocorrelation using the unit root test. So if we find, if we can use the unit root test to find whether there is a unit root. What is unit root? Unit root simply means that there is an autocorrelation of the magnitude of 1. That is complete autocorrelation. Usually we know the correlation coefficients lie between 0 and 1, right? Absolute value lies between 0 and 1. Here if the autocorrelation coefficient value is 1, we have perfect autocorrelation. That is the case of the unit root. So it is the perfect autocorrelation. The unit root is nothing but the perfect autocorrelation, and that we can test using the unit root testing. Okay, that we shall do later. Now let us consider only this. Okay. Similarly, now let us take the fourth variable Ri. Go to the variable correlogram. Here we have the unit root test. Okay, that we will do later. Go to the correlogram, and earlier, do you remember we have found that the variable Ri is not stationary. So let us take this correlogram. Again, 24 laps. Okay, click OK. And here we have the correlogram, ACF and PACF. And what do we find here? All the ACF values are highly significant. That is, we have 3 stars. 3 stars means they are significant at 1% level. So we reject the null hypothesis that the autocorrelation value is 0 at every lab. We reject the null hypothesis. And the PACF, the first 3 values are statistically significant. The first 2 values are highly significant, and the third value is significant at 5% level, and all other values are not at all significant. Okay, for the PACF. And see the Q statistic. We have the p-value of 0. That means we are rejecting the null hypothesis of 0 autocorrelation. Okay, so in all these cases we are rejecting it. And here what do we find? We know that the 2 red lines are the 95% confidence interval, and we find that we have used the 24 lags. Even by the 24 lags, the autocorrelation values are not coming between the 95% confidence interval. So whenever we have a situation like this, then we can conclude that the given series is a non-stationary series. It is a non-stationary series. That means there is full autocorrelation. There is not just autocorrelation, there may be a full or complete autocorrelation, perfect autocorrelation. That is, there may be a unit root in this particular variable Ri. a unit root must be there. So now see, this we say that this is a slowly decaying ACF. Slowly decaying ACF. If the ACF is slowly decaying, then it means that we have a non-stationary series. And in PACF we have one. This see, there is a significant spike. Okay, these are all insignificant spikes. All these are all insignificant spikes because they are all within the 95% confidence interval. They are all zero. But these three are significant. So these are all insignificant ones. Okay, these are all insignificant ones. And here these three are significant spikes. And the first spike is having a value of 1. Okay, having a value of 1. And it is actually an indication that we have one unique root in this particular series Ri. So the coronogram we can use to find out the number of unique roots usually. Okay, in general, okay, on an average, we can find out the number of unique roots also. If the ACF is slowly decaying, it is an indication that the variable is non-stationary, and the one significant spike with a value of 1 indicates that there is one unit root. Okay, that is the case. Now I shall take another variable. So this R. And let us go for the time series plot also, because earlier we haven't seen that. Take the time series plot, and what do we find? We have a number of crossings. We have a number of crossings. So this may be a stationary series, but we do not know whether this stationary series is white noise or not. And for that purpose, we shall find the coronogram. Go to the variable coronogram 24 lakhs. Okay. Now what do we find? See, okay, let us consider the coronogram, not the meshes. Okay. What we find is by the fourth lag, okay, by the fourth lag, the autocorrelations become zero, statistically zero, almost zero. Okay, in some cases, see here, one case we have 5% significance, and other cases are 10% significant. But those actually we can just ignore, because here by the fourth one it becomes zero. Or what we find in the ACF is a fast decay. A fast decay for the ACF. If we have a fast decay for the ACF or the PACF, okay, the PACF also is fast decay, then we can consider the series as a stationary series. But this is not a white noise. This is only a stationary series. This is not a white noise because we have 3 significant spikes here. 3 significant spikes here. So the autocorrelations are only fast decaying. All of them are not zero. If all of them are zero, then we have a white noise. So the difference between a stationary series and a white noise series is this. For a white noise series, all the autocorrelation values will be within the 95% confidence interval. But for a stationary series, we will have a fast decaying ACF. Okay, we have a fast decaying ACF. Now this, if we have a fast decaying ACF along with one significant spike in PACF, then we can tentatively conclude that this particular series R is an auto-regression process of order 1. So, an auto-regression process, that is a stationary auto-regression process of order 1. That is the indication of this. So, theoretically, we say that whenever the ACF is fast decaying and there is one significant spike in PACF, we have an AR1 process, auto-regressive process of order 1. And the case is the opposite for a moving average process. For a moving average process, we have a fast decaying PACF and one significant spike in ACF. One significant spike in ACF for an MA1 process. That is moving average process of order 1. Now, I don't have a theoretical time series for the moving average. Anyway, let us see this M, okay, and go to the variable time series plot, and we have a large number of crossings. So it must be a stationary one, and we do not know whether this is white noise or not. For that purpose, we go to the variable parallelogram 24 lakhs, okay, and this is what we find. And what we find is both the ACF and the PACF, we have one significant spike at 5% level. Okay, here there is a 10% level significant one, but we do not consider that. Or what we find is the PACF is fast decaying and there is a significant spike in ACF. Anyway, this M I have generated, see, all these variables are generated series, okay. I have generated this series as an MA1 process. So for the MA1 process, anyway, this lag is not significant at 5% level. That is the only case. So in general, remember that if the PACF is fast decaying and the ACF has one significant spike, then we have an MA1 process. So ACF, whether we have a AR process or MA process, we can also identify using the ACF and PACF. If the ACF is fast decaying and in PACF we have one significant spike, it is an AR1 process. If the ACF is fast decaying and in PACF we have two significant spikes, then we have an AR2 process. ACF is fast decaying and in PACF we have three significant spikes, then we have an AR3 process. The earlier ones I have just removed. Okay, doesn't matter. On the other hand, if the PACF is fast decaying and in ACF we have one significant spike, then we have an MA1 process. Similarly, if the PACF is fast decaying, we have two significant spikes in ACF, then we have an MA2 process. Or PACF is fast decaying, we have three significant spikes in ACF, then we have MA3 process. So it will continue like that. So ACF and PACF we can use for all these purposes. That is, we can identify whether a series is stationary or non-stationary. Also, among the stationary series, we can use the parallelogram to find out whether the stationary series is a white noise or not. Okay, and among the stationary series, we can find out whether the series is AR or MA with different degrees, different bodies using the parallelogram. Then among the non-stationary series also we can find out the number of unit roots using the PACF. if the ACF is slow decay. Okay, so these are all the cases that we have to keep in mind. Okay, now suppose I am taking this Rm. We go to the variable, then time series probe we have already seen. We have seen that this may be a stationary one. Let us see. Go to the variable parallelogram. We have 24 lags, okay, and this is what we find. So what is this? We find that the ACF is fast decaying, and in PACF we have 1 or 2 spikes, right? See, the second spike here is significant at 5% level, 2 stars. 1% level, 3 stars mean 1% level significant. These are insignificant because these are all significant at 10% level. We did not consider those, right? But so naturally one may say that this may be an AR2 process, right? Because the ACF is fast decaying and we have 2 significant spikes in PACF, so this may be an AR2 process. But theoretically, I generated this with as a combination of AR and MA process of order 1. That is AR1 and MA1. That is ARMA 1, 1. In ARMA 1, 1, we have both the properties of AR1 and MA1. So it will be very difficult to find out actually the orders of AR and MA in an ARMA process, because when we combine AR and MA process to get ARMA process, we are also combining the properties of both AR and MA. Remember, in AR, the ACF is fast decaying, and the significant spikes in PACF will give us an indication of the order of the AR. And just opposite is for the moving average. For the moving average, PACF is fast decaying, and the number of significant spikes in ACF will determine the order of moving average. So when we are comparing the properties of these properties. So it will be very difficult to identify the order of the ARMA process. We have to go for a large number of trial and error methods for fitting the ARMA process or for estimating the ARMA process. Okay? So where is it? What is this?
സാറേ അത് ഇടയ്ക്ക് വന്ന മെസ്സേജ്.
Anyway, I shall do allow, right?
അതെ, അലോ ചെയ്തേക്ക് സാറേ.
Okay.
അലോ ചെയ്ത്.
So I am closing this one, and this also I am closing. So okay. Now with this background, I think I shall go to the ARIMA model. Okay, now what is this ARIMA? I told you about ARMA only, right? ARIMA, the I in ARIMA means integration or the order of integration. Integration means non-stationarity. So non-stationarity, we have already found that, for example, taking this Ri, go to the variable and we have the parallelogram, 24 lags. What we find is this. We have very slow decaying ACF. Slow decaying ACF means it is non-stationary. And this shows that there may be one significant spike. If the significant spike will give us the number of unique roots, this one. So we can tentatively conclude that there is one unique root in the series. So if there is one unique root in a series, the series is called integrated series of order 1. We write I, then within brackets 1, I1, okay, I1. I1 means integrated of order 1. So this series Ri is an integrated series of order 1. That is, there is one unique root. Now, if we have a unique root, then we can remove the unique root by differencing. Okay, by differencing. So if we difference this series Ri, then the unique root will go and the series will become stationary. And we say that there is no unique root, or we say that it is integrated of order 0. We write I, then within brackets 0. I0. I0 means a stationary series. So let us, or before that, okay, we can find out the unique root also. Okay. So let us do the unit root testing. Go to the variable. Then here we have the unit root test, the ADF, augmented Dickey Fuller test. Click this. The unit root test usually we do in 3 formulations. That is, whenever, see, the series may have a trench or the series may not have a trench. Here in all these series, unfortunately there is no trench. Okay. Anyway, we click these first three. Okay. The last one is a modification by grading. We did not consider that. These 3. And we select that result depending upon whether the series has a trench or not. Okay, if there is no trench, then we can have this result, test without constant. If there is a trench, okay, linear trench, then we consider with constant result. If there is a non-linear exponential trench, then we consider this with constant and trench. So that is why we have these 3 formulations. Anyway, let us consider all these 3 for this variable. Okay. We have to consider this one, Ri. Okay. Then go to the variable unit root test, ADF. And here also we have to give the log. So keep it as 15 because it is given as default. Okay. And these 3 we are taking. Now we can use the level of variable, use first difference of variable. So first we are taking the level variable, and this is the level variable. Okay, Ri is the level variable, the variable given as such. So we click OK, and here we have the 3 results. The null hypothesis is A equals 1. A equals 1 means there is a unique root, or the unique root, the root is equal to 1. That is, the autocorrelation coefficient is equal to 1. And here we have the asymptotic p-value for test without constant. Okay, so consider only the p-value in all the cases. Now here we have 0.106, here we have 0.50, and here we have 0.29. In all these 3 cases, we have the p-value greater than 5%. If the p-value is greater than 5%, then we will not reject the null hypothesis. And what is the null hypothesis? Null hypothesis says that there is a unique root. So we do not reject the null hypothesis. Okay? So this is the result that we are getting. And that result, using the classical parallelogram, we find here. That is, the ACF is slowly decaying, and in PLCF we have a significant spike equal to 1. We have other two significant spikes also. We do not know whether these are equal to 1 or not. Okay. Anyway, now let us now remember, in doing the unit root test, we have to do continuously. With the level variable, we have found that there is a unique root. So what we have to do is we have to difference the variable one time. To difference this Ri, we go to the R, okay, R. And here we have first difference of selected variable. Just click it, and here we get dRi, that is delta Ri, the first difference of Ri. So now I am clicking this one. Go to the variable time series plot. What do we find? We have a number of crossings, mean reversions, so it may be stationary, but that is not enough. We have to do the correlogram. Go to the correlogram. 24 lakhs, okay. And what do we find? We have fast decaying ACF and one significant spike in PACF. Fast decaying ACF shows that the series is stationary, right? So the difference series is stationary. There is no unique root. Let us see whether this is the case with the unit root test. So let us go to the variable, and here we have the unit root test ADF. We are using all the three, okay. We know that there is no trend for the variable. Anyway, we are clicking it. See, we are using level variable because we have taken the delta Ri as such. So we can use this one. I shall show you. And here we have the three tests, and see the asymptotic p value. We have 3.153 E minus 50. Now see, the gradient is very clever to use the p value in terms of this exponential minus, negative exponential, because whenever we have E minus, just take it as 0. Okay, this is a very minute value, very close to 0. It is not writing 0, but giving the minute value, close to 0. But just remember, whenever we have E minus for the p value, E minus here also, E minus here also, take it as 0. And we know 0 is less than 5%. Less than 5% means we reject the null hypothesis of unique root. That means in the CDRI, that is delta Ri, first difference of Ri, there is no unique root. There we can stop. We can say that the variable Ri has only one unit root, and its first difference is stationary. That is, we write delta Ri is I0. There is no unique root. Got the idea? Okay. Now going back to this Ri. Okay. Oh, I have removed that. Okay. It's okay. Going back to the Ri, go to the variable unit root test ADF. Now what I am doing is, earlier we have already found the level variable results. Now I am using first difference. Okay, using the first difference. Click OK. We will have the same result. See, 3.153 E minus 15. We have the same result. So for doing the unit root test, these two options, that is variable, go to the unit root test ADF. These two options we can use, We need not go to the add and find the I. Okay. We can use level variable and then we can use for the same variable we difference. We will get the same result. So what we find is the first difference variable is stationary. Okay. And we can have a valid regression. We can have a valid regression only with a stationary series. With the non-stationary series, we cannot have a valid regression. The regression that we get is a spurious regression. So only with the stationary series we can have a valid regression. So the ARIMA model we can fetch using only stationary series. So for getting the ARIMA model, first we find out whether the variable is non-stationary or stationary. If it is non-stationary, then we have to find out the number of unit roots, and then we have to remove the unit root. If there is only one unit root, then we have to do one time differencing. If there are two unit roots, we have to do two time differencing, and so on. And removing the unit root and taking the difference to variable, we can go for valid regression estimation. So the ARIMA model we first do is, what we do in ARIMA modeling is transform the non-stationary series into a stationary series by differencing. And with the difference series, we apply an ARIMA model to the differential series. ARIMA model. So that ARIMA model to the differential series will give us an ARIMA model to the integrated series. So remember this particular point. An ARIMA model to the differential series will give us an ARIMA model to the integrated original level series. Okay, and in Gretel we can do the ARIMA modeling directly. If we are doing it manually, then we have to do it the way I have told you. That is, we have to difference the series and then fetch an ARIMA model manually. But in Gretel we can do the ARIMA modeling directly, including the degree of integration. That is, including d equals 1. We have here, in this case, we have one unit root. Therefore, we specify that d equals 1. So I shall show you how we do the ARIMA modeling. ARIMA modeling is a time-consuming one, but I am just remove this one. I shall just show for simple cases. Okay, I am taking this Ri. Okay, Ri is an integrated series. Go to the model. And here we have univariate time series. Remember, the ARIMA model and the Garch models are univariate time series models. We go to the ARIMA, and here we have the ARIMA model. Okay, the variable we are considering is Ri. Take that as the dependent variable and set it as default because we will have to do it several times. Now, if we have some independent variables, we can include it here. Then what we are getting is a vector ARIMA model. Okay, vector ARIMA model. But here we are doing only an ARIMA model. We do not have any independent variables. Now, whenever we are using a non-annual series, monthly data or quarterly data or weekly data and so on, there will be a seasonality in the series. So the ARIMA model we have to specify in non-seasonal ARIMA and seasonal arima. C-A-R-I-M-A. So the AR order we have to give here, I order, integration order we have to give here, MA order we have to give here. Similarly, we will have seasonal arima also. If we have a seasonal data, that is monthly data or quarterly data and so on. Anyway, in our case, there is no seasonality factor. Actually, we have to check it, but I am not going to do that. But remember, for this particular case, there is no seasonality, so I am not considering these cases. I will consider this non-seasonal. Let us consider this AR1. Okay, and we know that variable Ri has one unique root. Therefore, this I we have to write as 1. Okay, I is 1. And I am giving MA1 also. AR1, I1, MA1. So we can write arima 1, 1, 1. So this is the model that I can do. Now I am clicking OK. And here we have the result. And this result shows that the PHI 51 is the AR coefficient. Okay, AR1 coefficient. And this theta 1 is the MA coefficient. So in Gretel, we specify 51 as the AR1 coefficient and theta 1 as the MA1 coefficient. The MA1 coefficient is not significant. The 51 coefficient is significant here. Okay. Now for this particular model, we have to see whether the residuals are white noise or not. Okay. Or we have to do the test. Go to the test. We have the autocorrelation. Autocorrelation is we have to consider normality and arch also, but I am just taking autocorrelation. Okay, autocorrelation 12 flag, click OK, and the p value is 0.52, that is greater than 5%. Greater than 5% means there is no autocorrelation. Okay, so there is no autocorrelation in the residuals of this model. That means this model is adequate. This model is adequate. You can also try the normality test and the arch test. Okay. Now this is not enough. Now this theta 1 is not significant. So we have to do the modeling again. So I am going back to the model. Put this univariate arima. What I am doing is our Ri is still here. This MA1 is not significant, so I down it to 0, and AR1 I am increasing to AR2. So we have AR2, I1, MA0. So this is a model arima 210. Okay, 210, and then I am clicking OK. And what we find here is the second lag for the AR is not significant. First lag is still significant. And for this model also we have to find whether the series, whether the residuals are without autocorrelation. Go for the test. Autocorrelation. 12 lag. Okay. See, we have 0.5289. That means there is no autocorrelation. Okay, so this model also is significant. Okay, but we find that the second AR lag is not significant. So we go to the model. Univariate time series, arima. Now what I do is AR2 is not significant, so I down it to AR1. So now we have arima 110 and AR. Actually, this is an AR. The AR1 series for the stationary series. Okay. Now I click OK. So I have this one, and this also we have to see whether there is any autocorrelation. Go for the test. Autocorrelation. helpful arc. And what we find, the p-value is greater than 5%. If the p-value is greater than 5%, then that means there is no autocorrelation. So in all these three cases, okay, we have three models, three adequate models without autocorrelation. Okay, so which model we will select? And for that purpose, we have a model select. We have two model selection criteria. One is the using information criteria. Okay, using information criteria. And here we have three information criteria, Schwarz criteria. That is the Bayesian information criterion, then Akaike information criterion, then Hananquil information criterion. Usually we consider the Schwarz the Bayesian information criterion given here as Schwarz criterion. Okay, and we select that model for which the criterion value is the minimum. Okay, criterion value is the minimum. For this model, that is, we have the AR2 model. Okay, the criterion is 854. Okay, we have the 854.41. For this model, we have the Schwarz criterion 854.45, 1, 2. And the third model we have Schwarz criterion, that is only the AR1, 848.9437. So all these three models are adequate. 848 is greater than 854. For these two models, 854 is given. So for these two models, we have 854.418. And here we have 854.45. So this model we cannot select because this is greater. These two models, considering these two models, we have 854.41, 442. Here 854.45, which is less or minimum. The minimum one is given by this. Right? So we select this model. Now, these two models for the information criterion, these two models, the information criterion is only marginally different. Only marginally different. In such cases, we have to consider another criterion, another model selection criterion, that is the Occam's razor. Occam's razor says that we have to select a model as simple as possible. That is, as few parameters as possible. As few parameters means, suppose we have a model like this, and in this case, the Schwarz criterion is only marginally different from this one. Here we have three parameters. We are estimating three parameters. And here we are estimating only two parameters. So a two-parameter model is better than a three-parameter model. Or a two-parameter model is a simple model or simpler model than a three-parameter model. So we have to select this one. But in this case, the information criterion here is much larger. So we cannot consider this model. But among these two models, both the models are estimating three parameters. So we have to consider only this one. Because here we have marginally that the Bayesian criterion is less than this one. Less than this one. So it can so happen, okay. So sometimes we may have to do a large number of iterations like this, trial and error methods. So in this case, we write that Ri is an ARIMA 210. 210. What idea? So this is how we estimate an ARIMA model. We have taken a little more time. If you have any doubt, you can ask me now. Any doubt? Actually, all the participants are there.
ഹലോ, ആ സാറേ ഞാൻ അവരെ വിളിക്കാം. അജീന, ഹലോ.
The class started with more than nearly 60 people. Now it is only 38.
അല്ല 42 ഉണ്ട് സാറേ, 42 ഉണ്ട്.
Oh, I see.
അത് എനിക്ക് തോന്നുന്നു സാറേ, അത് ഈ ചില കോളേജില് അവര് ഈ ലേണിംഗ് സെന്റർ ഉണ്ട്. ഈ ലേണിംഗ് സെന്ററിലേക്ക് കയറി വരുന്നു. അജീന, ഹലോ, ക്യാൻ യു ഹിയർ മീ അജീന? ഹലോ ആൻസൽ കേൾക്കാവോ?
കേൾക്കാം സാർ.
അപ്പൊ ഇപ്പൊ നമുക്ക് ഒരു ചെറിയൊരു ഡിസ്കഷന്റെ ഒരു സമയമാണ്. നിങ്ങൾക്ക് എന്തെങ്കിലും ഡൗട്ടോ അങ്ങനെ എന്തെങ്കിലും ഉണ്ടെങ്കിൽ ഇപ്പൊ സാറോട് ചോദിക്കാം. ഇപ്പൊ നമ്മൾ അരിമയാണല്ലോ നമ്മൾ കണ്ടത്, അരിമ മോഡലിംഗ് ആണ് കണ്ടത്. അതിനകത്ത് എന്തെങ്കിലും, കാരണം അരിമയൊക്കെ നമുക്ക് പഠിക്കാറുണ്ട്, AR, MA, അർമ, അരിമ, ഇതെല്ലാം നമുക്ക് സിലബസിലുള്ളതാണ്. അപ്പോൾ അതിന്റെ അതെങ്ങനെയാണ് ഫിറ്റ് ചെയ്യുന്നത്, അരിമ എങ്ങനെയാണ് ഫിറ്റ് ചെയ്യുന്നത്, അതിന്റെ ഇന്റർപ്രിട്ടേഷൻ എങ്ങനെയാണ്, മോഡൽ അതിനെ സെലക്ട് ചെയ്യുന്നത്, അതാണ് സാറ് പറഞ്ഞത്. എന്തെങ്കിലും സംശയങ്ങൾ ഇതുമായി ബന്ധപ്പെട്ടുണ്ടെങ്കിൽ ഇപ്പം ചോദിക്കാം കേട്ടോ. ആൻസർ എന്തെങ്കിലും ചോദിക്കുന്നുണ്ടോ? ഈ പ്രൊസീജിയേഴ്സ് ഒക്കെ നിങ്ങൾക്ക് കാണാമായിരുന്നല്ലോ അല്ലെ? ഈ സ്റ്റെപ്പ് എല്ലാം തന്നെ നമുക്ക് നോട്ട് ചെയ്യാമായിരുന്നല്ലോ അല്ലെ? എന്തെങ്കിലും പിന്നെ കുട്ടികളെ ആരെങ്കിലും ഒന്ന്, സ്റ്റുഡൻസിനെ ഒന്ന് വിളിച്ചേ. സ്റ്റുഡൻസ് ആരെങ്കിലും എന്തെങ്കിലും പറയാനുണ്ടോ? അൻസൽ എന്തെങ്കിലും പറയാനുണ്ടോ? അൻസൽ
ഇവിടെ ഓക്കെയാണ് സാർ.
ഓക്കെയാണ്. ദേവിക, ഞാൻ ഒരാളുടെ പേരങ്ങ് വിളിച്ചതേ ഉള്ളൂ. ദേവിക ഏത് കോളേജാണ്? ഹലോ
ഹലോ സാർ.
ഏത് കോളേജാ ദേവിക?
കാത്തലിക് കോളേജ്.
ടീച്ചർ അവിടെ ഇല്ലേ? അജീന അവിടെ ഇല്ലേ?
മിസ്സിന് നെറ്റ് ഇഷ്യൂ ഉണ്ട്.
അപ്പൊ എങ്ങനെയാ ദേവിക, നിങ്ങൾക്ക് കാണാൻ പറ്റിയോ?
സാർ കാണാൻ പറ്റി. ഓക്കെയാണ്.
എന്തെങ്കിലും സംശയം ഉണ്ടോ നിങ്ങൾക്ക് സാറിനോട് നേരിട്ട് ചോദിക്കാനുള്ളത്? നിങ്ങൾ അരിമ മോഡൽ ചെയ്ത് നോക്കിയായിരുന്നോ? ആറിനകത്താണോ ചെയ്ത് നോക്കിയത്? ഏതിനകത്താ നോക്കിയത്? ഹലോ,
ഇല്ല സാർ, ചെയ്ത് നോക്കിയിട്ടില്ല.
ചെയ്ത് നോക്കിയിട്ടില്ല. ഓക്കെ. അപ്പോ എന്തെങ്കിലും സംശയം ഉണ്ടെങ്കിൽ ഇപ്പം ചോദിക്കാം കേട്ടോ. അൻസലെ, നിങ്ങൾ ഏതിനകത്തായിരുന്നു നോക്കിയത്? അരിമ ഏതിനകത്തെങ്കിലും നോക്കിയായിരുന്നോ?
അരിമ ഇതുവരെ പ്രാക്ടിക്കലായി ചെയ്ത് നോക്കിയല്ലോ സാർ.
നോക്കിയില്ല. അപ്പൊ ഏതായാലും ഇപ്പൊ അത് കണ്ടല്ലോ. ഓക്കെ. ജ്യോതിസ്, എങ്ങനെയുണ്ട്? നിങ്ങൾക്ക് എല്ലാം തന്നെ പ്രൊസീജിയേഴ്സ് എല്ലാം മനസ്സിലായില്ലേ?
ഓക്കെയാണ് സാർ, എല്ലാവർക്കും ഓക്കെയാണ്.
കുട്ടികൾക്ക് എന്തെങ്കിലും സംശയം ചോദിക്കാനുണ്ടെങ്കിൽ ഇപ്പൊ സാറുമായിട്ട് ഇന്ററാക്ട് ചെയ്യാം കേട്ടോ.
ഓക്കെയാണ് സാർ.
മിനു, അൽഫോൻസ കോളേജ്. ഹലോ, പറയൂ. നിങ്ങൾക്ക് കാണാൻ മിനു, എല്ലാം ക്ലിയർ ആയിരുന്നോ?
എല്ലാം ക്ലിയർ ആയിരുന്നു
സാറിനോട് എന്തെങ്കിലും ഇപ്പം എന്തെങ്കിലും സാറിനോട് എന്തെങ്കിലും ക്ലാരിഫിക്കേഷൻ വേണമെങ്കിൽ ഇപ്പൊ ആവാം കേട്ടോ.
സാറേ, ഞങ്ങൾ ഇതൊന്ന് ഡിസ്കസ് ചെയ്തിട്ട് നാളത്തെ ക്ലാസ്സിൽ ഡൗട്ട്സ് ക്ലിയർ ചെയ്താൽ മതി.
ഓക്കെ, അങ്ങനെ ആയിക്കോട്ടെ. ഓക്കെ. അജീന കയറിയോ അതിനകത്ത്? അജീനക്ക് എങ്ങനെയുണ്ട്? കാണാൻ പറ്റിയായിരുന്നോ? ഇത് ശരിക്കും കണ്ടിന്യൂസ് ആയിട്ട് കേൾക്കാൻ പറ്റിയായിരുന്നോ, കാണാൻ പറ്റിയായിരുന്നോ? ഓക്കെ. സാറിനോട് എന്തെങ്കിലും ക്ലാരിഫിക്കേഷൻ വേണ്ടതുണ്ടോ, എന്തെങ്കിലും ചോദിക്കുന്നുണ്ടോ? ഓക്കെ, അപ്പൊ നിങ്ങളൊന്ന് വർക്കൗട്ട് ചെയ്ത് നോക്കുക, എന്നിട്ട് നമുക്ക് നാളെ വേണമെങ്കിൽ വിശദമായിട്ട് ചോദിക്കാം. വിജയമോഹൻ പിള്ള സാറേ, അവര് കുഴപ്പമില്ലെന്നാണ് പറയുന്നത്.
അവർക്ക് നാളെ ചോദിക്കാം.
അതെ, അവർക്ക് നാളെ ചോദിക്കാം.